Hello, my name is Letty Ramos, and I'm a fourth-year physics major, and I work in the strongly correlated electron laboratory here at Fresno State. Today I'm going to be talking about some of the research that we're doing there. So I'm going to be talking about the phase boundary of the valence transition in the filled scudderite compound cerium, osmium-4, antimony-12 doped praseodymium. So filled scudderites are compounds with this chemical formula here, where for every one rare earth or alkaline metal, there are 4 transition metals and 12 nitrogens. So here's the unit cell diagram. These blue spheres represent the rare earth metals, in our case cerium and praseodymium, and they form a body center cubic sublattice. These red spheres are the antimonies, that's a nitrogen. They form a tilted octahedral sublattice with an osmium in each center, and these osmiums are the transition metals. They form a simple cubic sublattice. So the purpose of this study is to characterize the normal state resistivity and phase diagram for the valence transition in cerium, osmium-4, antimony-12 doped with praseodymium. The two concentrations, 10% and 20% praseodymium. So we're interested in this compound because it's been found to be an antiferromagnetic condo insulator in Eric Bauer's 2001 paper. So you can see the resistivity diverges at low temperatures. This is characteristic of a condo insulator, but recent data suggests this compound to be more of a semi-metal. The heat capacity graph shows a spike around 1 Kelvin. This means that there's a phase transition below 1 Kelvin, but the neutron scattering experiment showed this phase transition to be related to antiferromagnetism due to spin density wave formation. And Bauer also found the energy gap between the valence and conduction bands to be about 10 Kelvin for this compound. It is also a candidate to be a topological insulator, meaning that the whole Fermi surface and electron Fermi surfaces may coexist at low temperatures. However, this is purely theoretical, has not yet been confirmed experimentally, but the H-phase whole Fermi surface has been confirmed experimentally by this data on the graph on the right. Provided by my advisor and collaborators. This is the quantum oscillation frequency with respect to field direction in magnetic fields above 30 Tesla and temperatures below 4 Kelvin. So for this experiment, they placed the crystal in a strong magnetic field and then rotated it about several axes. That's what this field direction is. And then the quantum oscillation frequency was measured. And this is related to the Fermi surface because the charge carrier, in this case, the whole kind of orbits around the magnetic dipole moment. And so since the oscillation frequency is relatively flat with respect to field direction, that means that this Fermi surface is relatively isotropic. So a valence fluctuation is also known in elemental cerium as well as cerium compounds such as this one. And the valence transition occurs at low temperatures where the cerium ion permanently changes from a charge of 3+ to 4+ at low temperatures. So to determine the charge carrier per unit cell, there are 2 chemical formula units for every unit cell. And before the valence transition, when the cerium ion has a charge of 3+, the total charge carrier per unit cell is 2+. And then after the valence transition, when cerium exists as 4+, the charge carrier is 0. This is the phase diagram for the parent compound. So you can see at low magnetic fields, it's fairly sample dependent, but at higher magnetic fields, it starts to stabilize. This red dotted line is the valence transition phase boundary, where outside of it, the cerium ion exists with a charge of 3+, and inside of it, cerium ion has the charge of 4+. And this little orange hump at the bottom is the antiferromagnetism phase boundary. So this graph is made with a variety of different experimental methods, but the 2 that I will be talking about today are the maximums and minimums on the resistance versus temperature graph. So the minimums are along this blue data points here, and then our maximums are kind of where this pink dotted line is here. This isn't actually the phase boundary, but it's kind of a precursor to it because the experimental methods needed to find these data is a lot more difficult to do. So we're doping with praseodymium because it is the neighboring compound to cerium. So the ion exists as 3+ in this compound, which gives us a total charge carrier per unit cell of 2+, which is the same as cerium before the valence transition. So what we did was measured 5 samples, 2 10% samples and 3 20% samples in our cryo cooler, Fresno State. We measured it in zero magnetic field because we don't have that capability in our lab, and in temperatures between about 12 to 13 Kelvin all the way to 300 Kelvin. We did this with the 4-wire resistance measurement technique, where we send the current through the outer 2 wires and measure the voltage in between. And the resistance is related to the resistivity by these geometric factors, the distance between the voltage leads and the cross-sectional area. So the way that I found those measurements was by taking a very close-up photo of the crystals next to a millimeter graphing paper and taking the ratio of pixels to find the length between the voltage leads. And here's the side picture for the cross-sectional area. And then using that same crystal as an example, here's how I turn the raw data, the resistance versus temperature, into resistivity versus temperature with these geometric factors. So here's all the data that we took in our lab at Fresno State. On the left, we have all 5 samples. In the resistivity versus temperature, as you can see, the CRZ5 was scaled differently because its resistivity was much larger than the rest of them. We think this is due to a crack inside of the crystal so that the geometry could not be accurately determined from macroscopic measurements. And then on the right, we have the unitless resistance versus temperature for only the 20% sample. We measured one of the crystals twice after rewiring it because we could never find a minimum for this sample, and the minimums for the other 2 samples were quite inconsistent, unlike the 10% samples, which had a minimum of roughly the same point, about 41 Kelvin. And then we sent 3 of our samples to a collaborator in Japan who measured the resistivity versus temperature in magnetic fields varying from 0 to 14 Tesla. As you can see, the 10% samples showed maximums for some of the magnetic fields, whereas the 20% sample did not show any maximums, and our minimums occurred at roughly the same point for all magnetic fields for the 20% sample. So here is the updated phase diagram. In gray, we have the parent compound with 0 praseodymium content, and then this data right here is from the R minimums, and then this one's from the R maximums. So from this, we can infer that higher praseodymium content led to the phase boundary occurring for lower temperatures. And from this, we can infer that maybe the green sample had slightly higher praseodymium content. So for the 20% sample, though, no R maximums occurred. And this is probably because higher praseodymium content pushes the phase boundary to higher magnetic fields. We think this because this is the 0% sample, and then the 10% sample occurred at slightly higher magnetic fields, and then it was slightly higher for the green sample than for the blue sample. So for the red, the 20% sample probably occurs at a much higher magnetic field. So we also determined the energy gap. I did this using the logarithmic relation between unitless resistance and inverse temperature. And the energy gap is basically just the slope of the linear approximation for this a certain temperature interval on this graph. So here's kind of how I did it for magnetic fields of 0, 1, 2, 4, and 6 Tesla. But then I plotted the energy gap for all magnetic fields on this graph on the right. So for both of the 10% samples, it seemed to peak around 2 to 4 Tesla and then slowly decrease with a peak of about 14 and 12 Kelvin. And then for the 20% sample, it was seemingly constant, averaging about 3.7 Kelvin. And then for the parent compound, we just know that at 0 magnetic field, it had an energy gap of about 10 Kelvin. So in conclusion, increased hole doping shifts the valence transition phase boundary to lower temperatures, and higher magnetic fields. And future steps would include inspecting the praseodymium content of our samples with an SEM or EDX machine, and also measuring different concentrations of praseodymium, such as 5% or 15%, and then also to measure them in higher magnetic fields. That is all I have for you today. Thank you for your time.